Great. Well, welcome everyone. Welcome to today's webinar on guidance to make existing PV systems more resilient to severe weather events. And before we get started, I'm going to review just a few webinar logistics. Today's webinar is based on guidance from the Lawrence Berkeley National Laboratory, and you can find the infographic as well as a 4-page summary document and checklist summarizing the weather vulnerabilities and corrective actions, as well as pre and post-storm actions. And there's also additional resources you can find on gsa.gov. And we'll also be posting these links in the Zoom chat so you can access those directly. The full guide has not yet been published, but as soon as it's published, and that will be shortly, we'll be posting it here on the project page as well. Today's webinar, you're all in listen-only mode, but you can submit questions by using the Q&A button on the bottom of your screen. And you don't need to wait. The Q&A session will happen at the end of the presentations, but don't wait to submit your questions until the end. In fact, it helps us if you submit questions throughout the presentations. And today's webinar, as you'll note, is being recorded and it will be shared. You can find recordings for all of our webinars on our Outbrief webinar page at gsa.gov. And you can also access recordings on our YouTube channel. All of these are also posted in the chat window. And with that, I'd like to introduce Joe Skatch, who's the project manager and will be facilitating today's webinar.
Hey, good morning, everyone, or afternoon, depending on your time zone. Again, would like to welcome you to this presentation on solar PV resilience and addressing weather vulnerabilities. The information presented here was the result of the work over the past year with LBNL team, focusing on asset protection and preservation, risk-based assessment of those vulnerabilities, and helping to put together a maintenance program. Very much a privilege to work with this team, in particular, Gerald Robinson and Kevin Watson, who were the major researchers, primary researchers, and will be presenting today. Next slide, please. So very brief agenda here, introductory remarks, about 40 minutes for the presentation itself, delve into some detail, and then about 15 minutes for Q&A. And with that, I would like to introduce Mr. Kevin Powell, the director of the Center for Emerging Building Technologies, lovingly and fondly known as Green Proving Ground. So Kevin, take it away.
Thanks so much, Joe. And like Joe said, it's been a privilege to work with this team, including and especially Joe, who has done a phenomenal job on bringing this project all the way to this moment, to this closure, and to this presentation. Glad to have everybody here. Next slide. So the first thing, just as point of departure, PV is reliable, and I want to emphasize that. As you can see from this slide, 100,000 PV systems, 80 to 90% performing within the expectation, within spec, essentially. GSA has a number of arrays at this point with a reasonable amount of production, but I think, as everybody is aware, there's a directive to essentially get to 100% renewable energy for federal facilities in 2 years. We anticipate a significant number of new arrays, so we really want to make sure we get those right. Next slide. A couple of years ago, as you might all remember, there were a couple of just terrible hurricanes out there in the Caribbean, and I think, again, everybody knows what happened there. I mean, really serious storms. The thing that we found is we had two major systems, one in Puerto Rico and one in the Virgin Islands. One largely survived and one was completely destroyed. So in the after action from that, and both were completely built according to code. So in the after action, we asked Lawrence Berkeley Lab to do an assessment. What happened? What was the cause of failure? What could have been done differently? Next slide. That effort produced a couple of large reports. That is to say, they were very, very detailed, and they're very, very specific, and they're not public. And what we asked Lawrence Berkeley Lab to do is to translate that those two reports that were, again, very site specific and do what we do best at Green Proving Ground, which is to generalize results. So what the whole point of the Proving Ground is to take specific technology evaluations. Typically, of course, we're looking at happy stories where we installed something and it works well, and then generalize how we might deploy it more broadly. In this case, what we're looking to do is kind of the reverse, look at something that failed, understand why it failed and how to do that, how to prevent that kind of failure going forwards. And then as Andrea mentioned at the front, we're doing this with Department of Energy. The full report, the Department of Energy / GSA co-authored report, is still not released. It needs, it's in its final stages of review. There's a lot of review that happens on these kinds of reports, but we've really given this urgency around rolling out potentially a large PV initiative. We wanted to get some results out. So we published the findings in some infographics. You can find those on our website, and you'll hear all of the stuff that you'll hear following will be on this, as Andrea said, it'll be on a YouTube recording that you can again listen to afterwards. And so with that, I think it's time to turn it over to our LBNL team, Gerald Robinson and Kevin Watson.
Great. Next slide. Thank you, Kevin. So the team that did this work, shown here, myself and research associate Kevin Watson, who worked earnestly on this project. Also want to give a shout out to James Ellsworth of the National Renewable Energy Lab. He was a major contributor and did excellent work on costing some of our recommendations, which turned out very well. Before we get started and we talk about failures and start, I want to do some scene setting or talk about the market context so that we don't instantly move into a finger pointing session here. One of the sentiments I've heard from a few agencies is, how could my solar array that I've worked so hard for have failed in a simple thunderstorm where there was no tornado, where, we recorded 70-mile-an-hour winds, but our solar array is ruined. How did that happen? So the reason it happens to some is that the understanding in the industry in general is quickly evolving. So every set of storms presents new opportunities to learn. And we're facing, like any industry, where the codes and standards are on a different time scale. So revisions in a code might occur in a 5-year window. It takes industry a while to recognize an issue, deliberate through committee, and then present it to the next revision. And it could take a decade. So the industry's in that process right now. The other thing that's very clear is that I think the design community was taken by surprise at how unique solar structures really are. There is no comparable in existing code to point to and to grab lessons learned. So solar arrays, large surface areas mounted to lightweight structures, lightweight fasteners. The convention currently in engineering is going to assume static loading along, a single dimension, when you can imagine wind flowing through an array, very, very dynamic. So engineering does not quite represent what's currently seen in the field. I think the failures on top-down bolted joints that mount modules was quite a surprise. It's a chronic problem. And then there's growing understanding about the load paths with lightweight framing elements that flex in the wind. And what happens is they cause loads to transfer to fasteners and then to modules. And there's really a growing understanding that that's a problem. So the other thing that I would mention too is that data of failures is really siloed right now, siloed within insurance and siloed within big operators and system owners. So, the lack of data sharing has inhibited the ability to take quicker action. So moving on, so the issue of fasteners, without a doubt, for anyone that does this field work, which there are several people that do field work here and looking at failed arrays, fasteners always rises to the top as the most pronounced problem. So in the world of engineering, engineers don't really refer to fasteners, they refer to a thing called bolted joints. So what I mean by that is a bolted joint is really an assembly of bolts, washers, nuts, brackets, clamps, and grounding hardware that are all brought together to hold framing elements together or hold modules to racking assembly. So there are three types of bolted joints that we're going to talk about today. One is those that are used to mount modules to an underlying racking system, those that hold racking assemblies together, and those that are used to mechanically attach like a roof array to the roof structure or the building structure. We talk about critical bolted joints. Critical bolted joints simply means that should it fail, the structure will lose, or the system will lose structural integrity. So in a typical array, there are innumerous critical bolted joints all over the place. Each has unique issues that we discuss in the guide and try to help agencies kind of foresee problems before they become catastrophic. Again, this is just a real quick sampling of the types of common failures that we see, that we talk about in the guide. So this by means is just touching the surface. So, excuse me, in the racking assemblies, we have found the use of clamping fasteners, often inadequate, mechanical attachment points to buildings, either too few or too also inadequate. By the way, any agency that has ballasted roof arrays should take note, and those need to be examined. And then again, module mounting. There's a whole host of failure modes that occur with any one of these bolted joint types. The other thing that the guide seeks to increase awareness about is weather. A lot of people assume that weather really is, or severe weather is something of the Caribbean, something of Florida or the southeastern United States, and it's not. I've personally visited sites in New York, Arizona. So we're seeing failures occur at just routine weather. So that really is an indication of just how significant this problem can be for some and on some designs. So the guide tries to say, hey, agency, here's some resources. You can look up your location and really take stock of all the weather events that occur at your location and understand the types of wind speeds that are prevalent. So another thing that's occurring as climate shifts is that what we thought of as a 100-year storm is no longer that. It's more likely, something in the range of a 50-year storm. So people that talk about probabilities of a severe weather event refer to a recurrence interval. So a 100-year storm has a 1% chance of occurring in a given year. Over a 30-year system life, that's a 30% chance. Well, take what was a 100-year storm is now a 50-year storm. That changes from 30% to 60%. So the probabilities are getting much more significant as weather shifts. And it's not just the frequency, it's also severity of these storms is shifting too. Wind also seems to be the most complex and damaging weather event. It is generally talked about just as a simple wind speed. So engineers look up wind speeds for a location and they use that in their calculations. However, wind really depends on a number of factors. So for example, a tornado, even the lowest rated tornado of F0 at something 73 miles an hour will completely destroy the array, while a 73-mile-an-hour wind from a hurricane or a thunderstorm or a wind event in the mountains would leave the array completely untouched. So wind is a nuanced topic. Also, wind really depends on the site, the topography, the presence of trees, neighboring buildings, the characteristics, if you have a rooftop system of the building itself, height, parapets. I mean, it's a complex topic. So we also talk in the guide about the importance of working with a consulting engineer, because since the knowledge is not yet embedded in code, it's really important that you understand how to engage with an engineer that has the requisite skills and experience to address solar structures and bolted joints. So we're highly encouraging agencies, when they need the help of an engineer, which if you have a situation you're likely to need the help, is look for engineers that are actively engaged in committee work for example, the American Society of Civil Engineers now has a solar committee that's looking at structures. Many of those engineers are very active in the industry. They're very aware that you cannot just simply apply code. You need to do additional work as an engineer to produce a successful outcome. So next I want to introduce Kevin Watson, who's going to take us through the next section and talk about how to assess vulnerabilities. So Kevin.
Great, thanks, Gerald. Right, so I'm going to talk now more so on like the practical usability of the guide itself. And so when Gerald and I were writing the guide, we identified a little over 24 commonly known vulnerabilities that have been seen out in the field. And these came from our own experiences out looking at and surveying PV systems, as well as talking to other experts in the industry on this topic. And while we did do our best to try to identify the most common vulnerabilities, it's not entirely comprehensive, meaning that there is more than likely going to be a vulnerability that you may come across that's not represented in this guide. I would encourage that if that is the case and you do find a vulnerability that's not represented here, please let us know, because it's kind of just adding to this growing body of research of identifying and correcting vulnerabilities. And so within the guide, we identified we broke out the vulnerabilities into 4 different types. So we have structural, electrical, site management, and module specific. On the right-hand side is a screenshot of what the FEMP GSA, the full vulnerabilities guide, looks like. So this little screenshot on the right is showcases one particular vulnerability. So here, as an example, we have inadequate structural attachments to the building, one of the critical bolted joint issues that Gerald was talking about earlier. So we describe the vulnerability, kind of give you reasons on why it is an issue, provide some pictures kind of just showing what it might look like. On the upper right-hand corner, we have a risk impact assessment. And so basically what that means is, what is the risk if a vulnerability were to result in failure? So the vulnerability here being inadequate structural attachments to the building. If that vulnerability results in a failure, what is the safety, performance, and financial risks of said failure? We also have associated corrective actions for each vulnerability. We didn't entirely want to just be in the business of pointing out the issues. We also wanted to give practical corrective actions that you could potentially take into your PV system. And then at the bottom, we have field audit instructions. So it's kind of just a step-by-step way of, when you're in the field conducting a field audit, looking at your PV system to identify vulnerabilities. These are just easy instructions for you to be able to do so. So, for Gerald and I, it might be more straightforward on what to look for, but for the layman, it might be a little bit more complex. So we really wanted to make it as user-friendly as possible, because that is the point of a guide. Next slide, please. All right, and so we talked all about vulnerabilities. We'll talk about corrective actions. The one thing I really want to emphasize when you're out in the field is safety. That is one of the most important parts about conducting a field audit and being around solar PV systems. Particularly if you do suspect that your system is damaged, and that's the reason why you're conducting a field audit, you really want to make sure that you're taking safety with the utmost importance. So one of the best things to do is to bring along a qualified and trained electrical technician. They're going to be able to point to certain things that might be a hazard, like electrical shock hazards. And we put these little yellow electrical shock hazard symbols throughout the guide just to remind users that solar PV systems, like Kevin said, while they are very reliable, if there were to be, if they are damaged or you do suspect damage, you just want to make sure that you're proceeding with caution. Next slide, please. Right. And so the field audit is, we like to think about it broken out into two different phases. So the first phase would be the preparation of the field audit. The main thing that you're going to want to do is collect and review original documentation. And what I mean by original documentation is any of the original installation documents that your installer gave you. So that might be as-built drawings from the design and engineer, operations and maintenance manuals for the equipment, product spec sheets, and any performance reports. So any historical data on how the system's been performing itself. And what you're going to want to do, particularly with the as-built drawings, you're going to want to verify that the equipment that was specified in the as-built drawings was actually what was installed in the field. We've encountered discrepancies where the design and engineers specified, for example, they specified a certain thickness of metal for the substructure of the array. The installer substituted it out for a lighter gauge metal of the substructure. And if there is a discrepancy between what's specified in the as-built drawings and what's in the field, that could indicate a vulnerability. Like I said, with the thickness of metal, if you're in a hurricane-prone region, you're really going to want to make sure that your system is robust and you're not skimping on any material quality. And if you are missing as-built drawings, we'd recommend replacing them. So like Gerald was talking about hiring a consulting engineer, one of the benefits of doing so is that they can design and draw up new as-built drawings. And those are particularly useful for O&M contractors that are servicing the system, because they're going to want to know the size of the system. They're going to want to know all the technical components and products of the system. It's also really useful for implementing any major repairs later on, if that is the case. And then the second part is conducting the field audit itself. So like I mentioned before, safety is very important. When you go to conduct a field audit, whether you're traveling, just to your own site that you work at or to another state, you really want to the first thing you do is just do a high level assessment. Just walk around, look at the conditions of the system, really get a sense of what it's like, and take lots of pictures. Pictures are the best evidence, the best information that you're going to take back. And you can really never take enough pictures. And there's been often times where, we've gone out and done a field survey and we've come back to the office and kind of been like, oh man, we wish we had taken a few more pictures of certain parts of the system. So just want to emphasize that. The third thing I really want to point out is taking your time or allowing for adequate time. So making sure that you build in enough time to properly survey the system when you're out there, maybe build in another extra day if you're traveling, or a few extra hours to be able to go back to the office, look at the as-built drawings, go back into the field, look at the system. Because if you've ever been up on a rooftop in July or, in the middle of the winter, it can be really cold, really hot, it might be raining. You're going to want to just get the field audit over with as soon as possible. So really just make sure you're giving yourself enough time to do so. And then in the guide, we also provide different types of tools and equipment that can be used in conducting the field audit. Next slide. Right. And so we wanted to be mindful that even for a small system, like a 50 kilowatt roof mounted system, you might have thousands of the same individual components. So you might have, a couple hundred or thousands of module connectors, bolted joints, fasteners, hundreds of feet of wires that realistically you're not going to have the time or resources to inspect every component. So in the guide, we provided this this way of determining prevalence of a vulnerability. So it's basically identifying how common said vulnerability is. And we recommended checking different parts of different areas of the arrays, particularly because during the original installation, installers have different workmanship qualities. I used to install out in the field, and so working with other people have different ways of working and different quality levels of quality. So while one worker might be not adequately torquing and tightening fasteners in one section, the rest of the array might not be experiencing the same thing. So you want to check multiple areas so you're not just getting one bias in one particular area. Next slide. Right, and so Gerald had talked before about bolted joints as a key vulnerability. And one really great way to identify if bolted joints are a vulnerability of your system is to conduct a torque audit. And we provide directions for a non-destructive method of torque audits. And what I mean by non-destructive is that there's no industry standard for a torque audit in the solar industry. It's more so guidance taken from other industries like the automotive industry. So we wanted to recommend one that we thought was the safest method that would go to the greatest lengths to avoid the risk of damage to any fasteners. Next slide. And I'm going to turn it over to Gerald now.
Okay, thanks, Kevin. Next slide, please. So we want to talk about quickly, and again, this is a very cursory overview. The guide goes into much greater detail, but so here's a sample of some vulnerabilities with associated corrective actions. So everybody that's gone in the field and inspected system has seen what we call vibrational loosening of fasteners. So a structure exposed to wind will vibrate, and those vibrations in the bolted joint are quite powerful, and they will cause threaded fasteners to walk out and sometimes completely fall out. One corrective action might be to use locking hardware. I would mention that the understanding, at least my understanding of bolted joint issues has increased a lot thanks to some experts that I've been able to interact with. And oftentimes simple solutions like, use locking hardware really is not enough. There's systemic problems in a bolted joint, often design problems and other related problems. So just take what I'm saying with a grain of salt. There's often more to the story. However, let me just continue on. Racking clamp failures, the simple solution there might be through bolting. Module mounting, oftentimes you'll see inadequate strength in the clamps that are used to hold the module down. You'll find them bent open. So one option might be through bolting or upgrading to a stronger top-down clamp fastener. It's not always possible to through bolt a module. One note here is that module manufacturers have done a lot of testing. They have a lot of knowledge about how to best mount their modules. Some of them invested in wind tunnel testing. So you can consult the module manufacturer and you may get some good tips. The other one, again, is this mechanical attachments to the building structure. This is a particularly serious problem because it has obvious, very, very significant life safety issues. This would require an engineer to come in and apply best practice, which is, by the way, represented in some good guidance documents that are available. And that would result in adding mechanical attachments where needed. So I'm going to turn it back over to Kevin to talk about electrical.
Thanks, Gerald. Yeah, so I'm going to talk about the electrical site and module vulnerabilities. So the first vulnerability, electrical vulnerability, that I think is one of the most common issues I've seen across PV systems is improper wire management. And so with specifically on the DC wiring side. So those are the wires that connect the modules together, connect the modules to the combiner boxes down to the inverter. We've seen instances, for a number of years, the best practice was to use plastic wire ties. But if you've ever been out in the field, you know that those plastic wire ties degrade really, really quickly, particularly in high heat environments, which in any part of the country is going to be a rooftop system, ground mount, carport. Those areas get hot. And so those plastic wire ties break down very easily. They get very brittle. So the corrective action for that would be supporting any wires with purpose-built clips that can attach to the modules or to the racking rails. The second most common electrical vulnerability is inadequate electrical enclosures. So by electrical enclosures, I mean switchgear, meter boxes, transformers, things like that. Want to make sure that those enclosures are properly rated for the site's environmental conditions. So if you're in a hurricane-prone region, you want to make sure the enclosures are protected against wind-driven rain. If you're near an ocean, you want to make sure that your enclosures are corrosion resistant. The picture on the left kind of exhibits an inadequate electrical enclosure that's been rusted over time. So just making sure you replace those with the appropriate NEMA rated enclosure. The third one is equipment located below the site's 100-year flood level. So this is a really important one that we would recommend consulting flood maps from FEMA and the U.S. Geological Survey. Those maps are commonly being updated. I'm not sure annually, but pretty often. And you want to make sure that if any of your electrical equipment is located below the site's floodplain, you want to relocate or elevate the equipment above it. And we mentioned 100-year floods because there's quite a lot of information and maps out there, but we've also talked to contractors that use a 500-year flood level. So that would be an even higher elevation to relocate your equipment. And then the last one is damaged or improperly supported conduit. So you want to make sure that the vessel, the conduit that's carrying energized conductors is adequately supported and that the conduit fittings are rated for the site's environmental conditions. And so that would be accounting for thermal expansion, like contraction, expansion and contraction, and any moisture ingress. You want to make sure that you keep water out of your electrical enclosures. Next slide. And so with site vulnerabilities, the first one would be unobstructed wind forces. So there's a term called fetch, which is unobstructed wind forces coming from the ocean and that are typically not blocked by any building, tree, facility. And so those wind forces can have a significant impact on a PV array. So one recommendation would be installing a wind calming fence around the array to dampen those wind forces. Loose debris and equipment near arrays. You can see the picture on the left is a solar array in the Caribbean. What happened was during a hurricane, an old non-functional abandoned in place communications tower was toppled and fell onto the array. And that could have been prevented had that communications tower that was no longer functioning, it wouldn't have damaged the array had it been removed. So you want to make sure that you're clearing the site of any debris or abandoned in place equipment. The third vulnerability would be clogged drains. So this can be on a rooftop or it can be on a ground mounted system. You want to make sure that your drains are clear of debris because if you have a torrential rain or heavy snow buildup, you don't want that water buildup to flood back into your PV system and cause damage to the electrical components. And then the last site vulnerability would be poor stormwater management. So typically stormwater management features are implemented when you've just built the system, but there are stormwater management features that you can add post-construction. So some of those might be installing drains, bioswales, or pollinator plantings that are better able to slow the velocity of rain runoff and better absorb them into the plants. Next slide, please. And so the last type of vulnerability is module related. So the first one that we identified was modules that have an inadequate resistance to wind and snow loading, as well as hail impacts. So every module has a certain Pascal rating of what their resistance to wind and snow loading is, as well as hail impacts. And so if you have any concerns that you have damage, that your modules were damaged from wind, snow, or hail, we'd recommend testing the system on a whole, and then if necessary, testing string level and then module level if you've identified any performance loss. And we recommend replacing any modules that have a performance loss of 20% or greater. And when you're replacing modules, the first thing you want to do is make sure that the modules are technically compatible with the existing ones. But just in general, we would recommend modules that have an uplift rating of 3,600 pascals or greater and a resistance to hailstones that are 2 inches or greater. The last vulnerability is cracked or failed backsheets. And what I want to point out is that cracked or failed backsheets don't result from severe weather. They result from poor module materials. But when you have an open or cracked or failed backsheet, severe weather events like moisture ingress can go through the backsheet and interact with the semiconductors inside the module, and that can cause electrical shorts. And as you can see, the module on the left has a burn mark up at the top because it had a cracked backsheet and moisture got in. So we'd recommend replacing any modules with a module that has a certified bill of materials that's been tested in a third-party laboratory, just to make sure it lasts the full system life. Next slide. Right, and so also within the guide, as Gerald mentioned before, James Ellsworth from NREL contributed a great deal to the guide as far as the costing section. So there's really practical and very useful guidance on how to put a cost estimate together for a recovery or rebuild project. And these cost estimates are based on a variety of price adjustment factors. And so some of those factors are system type, ground, roof, or carport, system size, geographical location. And that's an important one because a rebuild project in New York is going to have a different cost than one in Oklahoma. And then ease of access. So if it's easy to get to the array or if it's more difficult to implement repairs or retrofits, that's really important as well. And then the last thing I wanted to say is we provide guidance on hiring a contractor. So Gerald talked about hiring a consulting engineer, which can be really useful in not only identifying vulnerabilities, but also putting together a repair scope of work. You want to make sure that you hire a contractor that has experience and skills in these recovery and rebuild projects, because they are unique when you compare them to new construction projects. So just make sure if you are involved in a recovery rebuild project that you're hiring a contractor that has the requisite experience for one of these projects. Next slide.
Okay, thanks, Kevin. So financing upgrades or repairs, that's obviously agencies are going to be concerned with that. In addition to the obvious choice of using appropriations, we wanted to point out a couple of other modes or avenues that you might not have considered. The other thing to realize about appropriations, while it's simple, it might delay by a few years the repair, which I'd argue some of them are pretty urgent, so you don't want to wait. But a couple of other options might be to integrate the cost of the repairs into an O&M contract, and that allows you to kind of put them on a schedule with the most significant and severe at the top. And often O&M contractors are very aware of some of these issues and are capable of making some of these corrections. I've seen one agency take kind of a troubled array, combine it with another energy project that also included more solar, wrapped it all together under one finance project, and was able to address latent problems while moving forward and doing more energy projects. That could be another tool. Another possibility is the use of the ESPC Enable Authority. Andy Walker from NREL has put together a white paper, I think should be released here at some point, talking about how that authority can be applied to O&M. So there's no reason why some of these, latent issues can't be swept up and included in that kind of contracting financing vehicle. Another thing I want to mention about the guide is that there's some helpful checklists, and these checklists are currently available on the GSA GPG website. And one of the things is, many of us are going to face the hurricane season, and there'll undoubtedly be a storm or two. So one of the discoveries that people who do field work have made is that, gosh, had I done certain things before the storm arrived, it would have at the very least been a sort of damage reduction strategy. So, for example, powering down all the components on the electrical side would reduce electrical shorts after a storm passes and the sun comes out. So we have this checklist of things you can do before a storm arrives and then after storm passes, and to reduce recovery time and cost. And then there's another checklist, which is just a summary of the entire contents of the guide, which is very handy. You can peruse that and get a sense of what's in the guide. Okay, so to recap, just some key takeaways from today's talk. Again, addressing bolted joint assemblies is, it's the most significant vulnerability. Identifying and correcting existing vulnerabilities to mitigate severe storm damage is another key feature of the guide. Knowing and understanding weather patterns at your location, conducting preparatory and recovery measures before and after weather events as a means to reduce damage and minimize recovery time and cost. And then another key takeaway of the guide is understand the importance of engaging qualified professionals that understand code gaps. That's critical. For federal agencies that would like some assistance or have some concerns, I encourage people to go to the FEMP Technical Assistance Portal and enter their request. And this is a quick turnaround. You'll be paired with a subject matter expert. You're also certainly welcome to reach out to myself or Kevin. And so those that are not, I suspect there's folks on this webinar that are probably in the private sector or in other public sector agencies. And we encourage you to reach out to us. There's contact information below. We'd also, if you have a story, we'd love to hear it. It helps us gain greater understanding. So next, we will go into our question and answer session. And Andrea, did you want to?
Yes, and Joe will be facilitating that, and I think he'll be. I think we have a lot of great questions, and so we'll get through as many of these as we can in the next 15 minutes.
Yep.
Okay.
Great. Fantastic. Okay. Here's the first one. Is there an advantage from the structural issues noted to locate solar panels on the ground versus on elevated structure, roof, etc.? Is there evidence of locational damage that should feed into the process?
This is Gerald, I'll answer that. Well, absolutely. There is, well, first things, I work on distributed generation projects, right? So I work on projects that are on site. So there probably is a different discussion to be made for utility systems. Most agencies don't really have the luxury, they're somewhat space constrained, so they don't really have a choice. But where the array is located will influence. It's, so for example, if it's in an area that is has unobstructed exposure to the wind, that would naturally experience more damage than one that would be adjacent to building structures, or a lot of vegetation is known to break up wind forces. But I would say that I do believe that regardless of the site, a good durable, weather toughened array can be placed. So, but it has to be done with qualified engineer and contractor. So.
Okay, great. Next question. Is system framing typically galvanized steel?
Yeah, that's the most common metal. Yeah. Cold rolled structural channels are the most common framing type used, and they're galvanized.
Okay, next question. What about the use of something like Loctite as a thread locking adhesive? I'm sure the team looked at various practices, and vibration is always an issue.
Yeah. So that Loctite is certainly a legitimate method of securing fasteners. There's products. There are bolts that come pre-applied. So when you actually install them, the thread locking material breaks open and spreads into the threads. There are some trade-offs with thread locking adhesives. So because bolted joints in the field, naturally, the bolted joint engineers refer to it as a phenomenon of relaxation, because the metals mate over time. There's thermal expansion. The thread locking doesn't allow readjustment. It doesn't allow torque auditing. And also, based on what I've seen in terms of types of materials that do well in the field, I'd be suspicious if the thread locking adhesives would survive for the long term. I would be cautious. There are other options, so I wouldn't feel compelled to naturally seek a thread locking adhesive as a first choice.
Okay, great. Are there Category 5 wind calming fences?
Well, okay, so a wind calming fence is an idea that some of us are kicking around because it's not a new technology. It's an old technology. It's used out on the Western Plains to manage snow deposition, prevent snow from depositing onto freeways, causing havoc. So, Category 5, obviously that's the highest rated hurricane. It's certainly, I've seen low-end Category 5 structures, or structures survive low-end Category 5 events, but it's I think what the question is, can you build a fence that would survive a Category 5 event? Perhaps at great cost. So I'm not really sure how to answer that. That's a tougher one.
Okay, next question. Have you found evidence of poor workmanship? What advice do you have to manage and inspect workmanship?
Oh yeah, workmanship is obviously a core issue, and absolutely have seen it. I've seen, and again, I don't want to pick on the solar industry because that wouldn't be fair. It's something that happens, right? So I've seen, cutting corners all over the place, substituting materials, as I think Kevin mentioned earlier. The way to manage that is to really make sure that the contractor has qualified installers, trained, supervised, and then one very, very important step that people will forget or gloss over is commissioning. I can't stress that enough. If you treat commissioning as just a checklist exercise, you're not going to get the results. But commissioning is a really, really good step in catching some of these workmanship problems, which could result in catastrophic outcomes. Okay.
Next question. Do you have any suggestions for quote unquote out of the box designs to reduce the risk of failure, i.e. design concept for the installation or designs of the components and connections, i.e. design concept for the installation or designs. Oh, I'm sorry, that was a repeat. So design concept for the installation or designs of the components and connections. Are there out-of-the-box solutions that can help mitigate damage?
Out-of-the-box solutions. Well, I don't know if this is a new construction question or an existing system question, because we're largely here focused on existing systems, though, you know, what we're saying here does have implications for new construction. You know, a lot of racking manufacturers racking systems are factory made, right? They come from a factory and they're assembled in the field, sometimes partly assembled in the factory, partly assembled in the field. I would answer that question by saying I think there's a lot of innovation yet to go. I don't mean to say this disparagingly, but I do believe right now we're kind of in the Wild West of solar. There's a lot of goofy stuff that I see in the field, and that means I think there's a lot of innovation in design and cost reduction yet to come. So I don't know if that answers the question, but that would just be my general observation.
Okay, next question. Is there a SOW or list of items to be screened to perform maintenance of a PV system, particularly related to ESPC, related to an ESPC related project?
The individual may be asking about third-party systems or an ESPC where the vendor has the responsibility for O&M, or the ESCO has responsibility for O&M. That's a good question. We are working on O&M materials right now. We have one resource already posted on the FEMP website, which is a templated document. There's a lot of good information in that. We're working on a second one, which is a supply schedule based solution. So I think that might address your question. If not, feel free to reach out to me and I can, you know, certainly, by the way, I would mention there, you know, even if someone else is doing the O&M or it's not part of the, you're not really the system owner, you should know a little bit about safety, especially if it's a roof system. You should care about that. And there's certain things you can kind of keep an eye on. So.
Okay. What is an electrical purpose-built clip that you would recommend, type or manufacturer?
Oh, Kevin.
Yeah, I can take that. I wouldn't have any particular manufacturers I'd recommend, but if you, I hate to be that guy, but if you Google PV module clip, you'll see different components. There's some that are just small that can hold 2 individual module wires that clip directly to a module. Like if you've held a module, there's the aluminum or steel frame around it is pretty thin, and so you can clip the module to there and then pop some wires. There's also bigger clips that attach directly to the racking rail where you can put the module wires in those. So yeah, my recommendation would be to just do a little quick internet search on just typing in PV module clip or PV module cable wire clip, something like that.
Yeah, I've noticed that some racking manufacturers make their own.
Right.
Will offer it as part of the kit. They're not used necessarily, but then there are others that are just generic that clip into the side of a module or on its frame that aren't brand specific.
Yeah.
All right. Have you or anyone used SmartVolt's color changing for visual indication of torque verification instead of a manual torque audit?
Yeah, okay, so what that person's referring to is that there's when you tighten the bolt, there's a little section on the top of the bolt that will change color when you've reached the proper torque value. So that fastener is purchased ahead of time with that functionality. They're very expensive. I've not used that. That could be one way of dealing with the anomalies in the field with installers, right? Because installers just use impact drivers and they don't have any meted torque value from an impact driver. Matter of fact, you may over tighten. So this could be one way to get a visual indication that you've reached the proper torque level. So Yeah, but I don't have any experience with that. But there are voltage joint engineers that there's a white paper out, I think, by Next Tracker, put a good white paper out on that topic of various options. So I'd look for that.
Okay, next question. Is there a water resistance rating in parens IP code that is recommended for the junction boxes or inverters?
Kevin, did you want to?
Yeah.
Did a lot of.
I don't have a specific, I don't think I have a specific answer for that. I would say for the inverters, inverters are actually pretty watertight. I don't think that they would hold up during a flood, but I don't know what enclosures really would. As far as junction boxes go, I would look and make sure that you have junction boxes that have proper like rubber gasketing around them to make sure that that prevents any moisture from getting in. It's also, to kind of get a little bit more in the weeds, when you have junction boxes, oftentimes their installers will install them face up, and so you take the screws out and open the junction box cover off and get to the wires and components inside. I think it'd be better if you're in an area that gets a lot of rainfall or gets a lot of snow or moisture, is to just position it so that it's more horizontal and that the face and the openings are not exposed directly to the rain or snow.
I wonder if the question is about like a NEMA rating on cabinetry, maybe like NEMA or something.
Okay, right. Yeah. If that is the question, then I think the minimum NEMA rating would be a NEMA 4, and if you want to make sure that it's corrosion resistant, it's NEMA 4X. I'm not 100% sure what inverters are rated within NEMA.
A lot of balance of system equipment like switchgear and things come with just sort of a standard cabinet, but you can choose different cabinet options. I don't know if that's available with inverters. I doubt it, but with all the other balance of system equipment, you can choose the rating on the cabinet that's used. And by the way, keep in mind that it's the guts of what's inside the cabinet that's valuable, not the cabinet. So spend a little more money on the cabinet is a good choice in expense.
Okay, great. It looks like that's going to be all the time that we have questions for. Any of the other questions that came in, the team will try to get those answered at a later time, but we covered a very good amount of them. Thank you very much for those great questions. And if you have them, you can still put them in there. Kevin, do you have any closeout thoughts or words that you want to share?
I wanted, but while Kevin gathers his thoughts, I also want to jump in to say that we will be sending out a survey, and you'll receive that tomorrow. And we're looking for experience. If you have experience and can share any of your experience on storm damage, as Gerald and Kevin said, we're looking to gather a bigger data set, so that's helpful. And also, if you're looking for technical assistance, you can also put that in the survey and we'll reach back to you.
I was so confused because of the other Kevin. I didn't realize you were talking.
That's right.
This Kevin.
Two Kevins, yes.
So I do want to just thank everybody for having joined us on this webinar. And this all started, in fact, really with this notion that a 10-cent locking washer would have prevented millions of dollars of damage, essentially. So I think the message is, we have some expensive assets. Let's make sure that they're going to last for the long haul, and we truly aren't penny wise and pound foolish.
Great, thank you. And there's just one quick question that someone asked for the company name, that white paper on torque testing, I think on the bolts that you mentioned, Gerald. What was that company name again? And we'll put it in the chat.
Oh, okay. So Next Tracker and John Ness of Matrix Engineering put out a really nice white paper on fasteners.
Okay, great. We'll put that, send that out in our follow-up email as well.
Okay, yeah.
Great. Thank you, everyone. And thanks so much to the panelists and to all your great questions, and look forward to seeing you on the next webinar. Bye.